Remember this circuit. This is a parallel adder. This is the A input, A0, A1, A2, A3, and the B input, B0, B1, B2, B3. This is a 4-bit parallel adder. This is the output of the parallel adder, and this is the final carry that goes out of the parallel adder. This is the carry in, the Cn that goes in here. Let's modify this circuit to make it work as a parallel adder or a parallel subtractor, depending on what we put here on this control input. The modification is like this. If we add these exclusive ORs as an input to the full adders here, okay, and we put a 0 on this control input here, this 0 goes into the C0 of this full adder, so this become a parallel adder because here the 0 makes the B0 goes into the input here, and the input here is B1, and here B2 and B3. So what you have now with M equal to 0 is an adder that adds up 4 bits. Now if we change M into 1, what happens? Here we have B bar instead of B. Here we have B0 bar. Here we have B1 bar, B2 bar, B3 bar. So we have the ones complement here, and this C0 is equal to 1. So what happens is that we have the 2's complement of B added to A, which means the output here is equal to A minus B. Now let's talk about something called the overflow in addition. Assume that you want to add 2 numbers. Each number consists of 3 digits, or in binary in 3 bits. This is a 3-bit number, and this is a 3-bit number. If we add them, we get this result. You notice that the result is a 4-bit number. In this case, we have an overflow. So an overflow is when you add 2 numbers, each with n bits, and then the result will be n plus 1 bits. This might be a problem in digital systems. Now let's look at a case where we have no overflow. Suppose we want to add this number, which is 2, and this is number, which is 3. These are signed numbers. This is a 4-bit number. The last bit here is the signed bit, so this is a positive 2. And the last bit here is 0, which means this is a positive 3. If we add them together, we get positive 5. The parallel adder will do it this way. This number will be put on as an X input, and this number will be put as a Y input. Now, the S will result here, and the final carry, which is C4, will be 0. Now, the answer is correct. It's a positive 5, because if you add 3 and 2 positive, you should get a positive 5. Now let's take a case where the overflow occurs and see how this is a problem in digital systems. Now if you add a plus 5, this is a plus 5 as a 4-bit number. This is a plus 5, and this is a plus 6 as a 4-bit number. Now the answer should be plus 11. This is a plus 11. Note that the answer has 5 bits, not 4. So an overflow occurred. Now this number 5 is put as a Y input to the parallel adder. This 6 is put as an X input to the parallel adder. What you will see at the output here is 1101, which is this, and the carry is 0. So this is a signed number, which says that this number is negative. So that is the answer here is not correct unless we take this here as a signed bit. So something has to tell me that an overflow has occurred in order to verify that the final result here is the correct answer. Let's take another example for the overflow condition. This here is minus 5. This is a minus 5. Remember that the numbers in the signed notation is 2's complemented. So this is minus 5 and this is minus 7. if you add them together, you should get a minus 12. This should get a minus 12. Now remember, minus 12 here is 5-bit number. So an overflow has occurred. Now this 5 goes here, this 7 goes here. Now the parallel adder will make the addition, and this is what you will see on the S output, and the carry here is 1. If we this one here, this bit here is the sign bit. If we look at it as the sign bit, then the answer would not be correct. So something has to tell me that an overflow has occurred, and this bit here is the sign bit and not the carry. If you notice in the first example, in this stage, we have a carry from this stage into this stage. 1 plus 1 is equal to 0 and a carry. While in this stage, we have a 1 plus 0 plus a 1 plus a 0. That's a 1, and there is no carry. So we have a carry from this stage into this stage, and we do not have a carry to the final carry. Also, in this example, in this stage, we have no carry from this stage into this stage. While from this stage into the final carry, we have a carry. So there is only one carry, either from this stage to this stage, or this stage to this stage. In these two cases, we have an overflow. So how do we find out that we have an overflow? We take the carry from the stage before the last and the final carry into an exclusive OR. If the output is equal to 1, that means the result here is not the true result. You have an overflow. If there is a carry from this side to this side and no carry here, then this V will be equal to 1. One of these two carries, C3 or C4, has to be a 1 to make V equal to 1 to indicate that there is an overflow, and a consideration must be taken in looking at the final output, since it is not the true output. You must take care of the sign bit and the carry. Okay, let's build a BCD adder. What's a BCD adder? A BCD adder is a device that adds two BCD numbers together along with a carry input to give me a sum of a BCD number here. So what we have here at the first input is a BCD number that ranges from 0 to 9, and another BCD number at the second input that ranges from 0 to 9. Now a carry that ranges from 0 to 1. So a total sum that ranges from 0 to 19. Why 19? This is 9 and this is 9, and this could be a 1. So there should be here a 19. How would this 19 appear? It will appear here as a 9, and this here will be considered a 1. So this is 19. This is the output of the BCD adder that I want to build. These here are the output here, and this is the will appear on the C. This is 0, 0. This is 10. This is 16. This is 17. This is 18, and this is 19. Now, the binary equivalents for these BCD sums here are these, okay? This is here in binary. This is 0, 0 in binary. This is 0, 0 in binary. This is here 0, 9 in binary, okay? And this here is 10 BCD in binary. This is 8, this is 2, that's 10. That's equal to this. This here is 19. This is 16 plus 2 plus 1 is equal to 19. We notice that in this area here, the BCD sum and the binary sum, they are equivalent. They are the same. So if I use a binary adder, a parallel adder, in this area, the output here will be the same. It's equal to the BCD number. However, in this area, they are different. So I have to adjust the output. If I want to use a parallel adder, I have to adjust the output here to look this way. And how do I do that? I do that by adding 6. If I add 6 to each one of these, I will get the equivalent BCD here. Look, add this number here to 6. You will get 10 in BCD. Add this number here to 6. You will get 11 in BCD. Add this number in binary to 6 in binary, you will get BCD 19. So if I use a parallel adder, I put the first number here and the second number here, and I use the familiar parallel adder, I will get the result here in this area the same. But if I take the output here and then I add 6 to it, I'll get the sum here in BCD, knowing that the carry to the second parallel adder here is equal to 0. This one here. BCD number 1, BCD number 2, okay, the carry, whatever the carry is, connect the output of this parallel adder into the first input of the second parallel adder, and then here you put a 6 at the other input, making sure that the carry to this adder is 0. Okay, you will get the BCD adder. But now you have to decide when to add 6. Okay, this is the area when you add 6. How do you find it out? Look, what is common in this part is that the K here is equal to 1. So whenever K equals to 1, you add 6, you will get the proper BCD output. This area here, it has something common. That is Z8, which is this, and Z4, which is this. They are 1. They are only 1 in this area. Okay? So whenever you have both Z8 and Z4 equal to 1, you add 6 to get the corresponding BCD number here. This area is characterized by Z8 is equal to 1 and Z2 is equal to 1. So in this area, whenever Z8 is equal to 1, Z2 is equal to 1, add 6, you will get the proper output. Okay, so you draw the circuit. This is the first binary adder. Take its output as an input to the second binary, and then add 6 here. But now this 6 is controlled by whenever K equals to 1, or whenever Z8 and Z4 equals to 1, or whenever Z8 and Z2 equal to 1, then take the output of this OR gate into this position here. You will have a 1 here, and you will have a 1 here. Connect a 0 here, connect a 0 here. So this 6 is added if and only if you have an output here which satisfies the conditions that we talked about, K being equal to 1, or Z8 and Z4 equal to 1, or Z8 and Z2 equal to 1. Okay, and this is the BCD sum, which is sum 0, and here is the BCD sum. Okay, let's take an example on this one. On this circuit, this is a 9 here, this is an 8 here. The output of this binary will be this one, and K will be equal to 1, and K equal to 1 meaning the output of this gate is equal to 1. A 6 will be added here to this number. If you add 6 to this number, what we will have here is this, which is BCD 7, and this is 1. So the output 9 plus 8 is equal to 17. This is 17. 1, 7. Another example, this is 5 plus 6. You should get an 11. In binary, we will get this one here at the output, and then we will have a 1 here because of this condition here. That means this number will be added to 6 to get a 1 here and a 1 here, which makes up 11.